All right, going to be working the next section, and that's going to be the section on graphing tangent, cotangent, cosecant, and secant functions. And we're starting out here with number 7. It says, what is the y-intercept of tangent x? Of y equals tangent x. So it wants to know when the tangent function is 0. Or sorry, y-intercept, not x-intercept. The y-intercept, in order to find y-intercepts, what we do is we set x equal to 0. So on the graph of tangent, you should actually know what the graph of tangent looks like from class. You have these vertical asymptotes at pi over 2 and negative pi over 2. But the graph goes like this. And so the y-intercept is that point right there. Now to get it, we just plug in 0 for x. And tangent of 0 is on the unit circle, is 0 degrees. It's the y-coordinate divided by the x-coordinate. So the y-coordinate divided by the x-coordinate is 0 divided by 1, which is 0. So that corresponds to when you plug in 0, you get 0 out, so your y-intercept is 0. All right, that's number 7. Number 9. What is the y-intercept of secant x? All right, so what is the y-intercept of secant x? Again, you should know what the graph looks like, but yeah, let's do it with the graph and then I'll do it algebraically. The graph of secant x, what we do to get the graph of secant x is we remember that this is 1 over cosine of x. And so what we do is we start out by graphing the cosine function. So here's 1, here's negative 1. The regular cosine function would go like this, then back up, and it would stop here at 2 pi. And then it would go backwards doing the same thing like that. Okay, so that's cosine x. And then wherever this hits the x-axis, we have vertical asymptotes. So we have vertical asymptote here, vertical asymptote here, and we have vertical asymptote here. And then what we do to draw secant is we go to the top of cosine here, and we draw almost like a little parabola. Then we go to the bottom of the cosine function there, and we draw almost like a little parabola. And then this one over here would go like this and come on this side, and we'd have another one over here going like that and like that. But what we want to know is the y-intercept. So it looks like it hits the y-axis at 1. Now how could we get that? Well, to find the y-intercept, set x equal to 0. So if we do that in here, we get 1 over cosine of 0. And of course, cosine of 0 is 1. So we get 1. So we should hit the y-axis at 1, which is what happens. All right, number 11. 11, for what numbers x we want our x to be between negative 2 pi and 2 pi. For what values of x between there and there does secant x equal 1? All right, so we could graph secant, I just erased it, but oh well, we'll try it algebraically. So when does secant x equal 1? Well, this is the same as asking when is 1 over cosine x equal 1? And if I multiply both sides by cosine x, then I get 1 equals cosine x. So where is cosine x 1? So we're going to go back to the unit circle, and we're asking ourselves, when is the x-coordinate 1? Because remember, cosine of an angle is the x-coordinate on the unit circle. And the only place that the x-coordinate is 1 is here. Right? That's the only place the x-coordinate is 1. So that angle is the angle 0. You could also look at it as 2 pi, or you could look at it as negative 2 pi, or you could look at it as 4 pi, or negative 4 pi. Any of those would work, right? And they only want the answers between negative 2 pi and 2 pi. So that means 0 works, 2 pi works, negative 2 pi, but these are too big. So those are our only answers. Those are the only places where secant is 1. Hold on. Did I write that down right? Secant. Oh, yes. Okay, that's where it's equal to 1. I apologize, I read the problem wrong. Now it asks for what values is it negative 1. So when we want to know when it's negative 1, it's a separate question they're asking. When is secant x negative 1? We want negative 1. We want to know when 1 over cosine x is negative 1. Then we can do our multiplication on both sides again. We get negative cosine x on this side when we multiply both sides by cosine x, and then divide both sides by negative 1. You get cosine x is negative 1. So when is cosine negative 1? So where on the unit circle is our x-coordinate negative 1? That happens here. And that angle you could look at as being pi, right? To get there is pi, or you go backwards, negative pi. You could go pi, 2 pi, you could go 3 pi. You could also have gone negative 3 pi, you could go 5 pi, negative 5 pi. But the only answers that live here are these two right there. Everything else is too big. So these are the answers to the first question of when is secant 1. And then this is the answer to the second question of when is it negative 1. Only between negative 2 pi and 2 pi. All right, moving on. We are on 13. All right, for what values between negative 2 pi and 2 pi does the graph secant x have vertical asymptotes? So we're only again looking between negative 2 pi and 2 pi. It wants to know where secant x, where does this have vertical asymptotes? Well, vertical asymptotes are going to occur whenever this is 0, because then we'll be undefined. So you're really asking the question, when is cosine 0, when is cosine x equal to 0? So if you go to your unit circle, you're saying where is the x-coordinate 0? And that actually happens here and here. And we need all the possible answers that live inside, or that are between negative 2 pi and 2 pi. So let's get all the ones between 0 and 2 pi. So if I go around counterclockwise, I get that one right there, that's pi over 2. Then I've got pi, this is 3 pi over 2, so 3 pi over 2 would bring us straight down. And then we come around 2 pi, we have to stop. Then we could go backwards. We go from here to here, that's negative pi, so negative pi over 2. And then I go around, that's negative pi, that's negative 3 pi over 2. So those are the only answers that I have between negative 2 pi and 2 pi. All right, 15. Where does the tangent function have vertical asymptotes? Where does the tangent function have vertical asymptotes? Now I'm going to leave this up here for a second. Number 15, it's same interval. It wants to know when does tangent x have vertical asymptotes? Vertical asymptotes, when does that happen? Well, tangent is sine over cosine. And the only way that this is ever going to be undefined, which is where we have vertical asymptotes, is if that's 0, if cosine is 0. But that's the same question we just asked. Okay? The only difference is not a 1 on top, this time it's sine. But to get undefined, the denominator is what matters. So that's only going to happen again here at pi over 2, 3 pi over 2, and negative pi over 2, negative 3 pi over 2. All right, we're good. 17. Finally, we get to graph. So graph each of these functions. Y equals 3 tangent x. Okay, so what you have to do these is you have to know what tangent looks like. Okay, so you have to know that the basic tangent function has 2 key points. I should say 3. Negative pi over 2, pi over 2 are where we have our verticals. And then we have the x-intercept right there, like this. So that's what tangent looks like. Kind of like when we were doing sine and cosine, we had these important points. Well, here we have 2 important vertical asymptotes and then an x-intercept. So what we do is we set the argument x equal to the 2 important points, negative pi over 2 and then we set x equal to pi over 2. And now I'm going to go draw my graph. I know that at pi over 2, negative pi over 2, I have something important happening. Well, because it's the tangent function, that should be vertical asymptotes. Then I know midway between these two, I have an x-intercept, and that's at 0. And then it's just really a matter of determining now, does it look like this? Well, what does the 3 do to this graph? Well, since it's a positive number, it doesn't flip it over. If it was negative, it would make it look like this instead. It would bring this piece down and that piece up. So I know it still looks like the purple one here. It's just, what does 3 do? And we talk about this in class. If this number right here is bigger than 1, it stretches it out. So maybe the regular tangent function would have looked like this. Now just imagine stretching it. So like instead of this piece, it's going to look more like that piece. And instead of down here, it's going to pull things down, so it's going to look more like that. And I'm not real particular about how good this looks, because these vertical stretches on the tangent function are hard to graph. So this is basically in red what I'm looking for. Okay, that's it for number 17. Let's look at number 21, tangent of pi over 2x. Yeah. All right, so same story. We have a tangent function. The important points are the two ends in the middle. So I'm going to take the argument here, pi over 2x, set it equal to negative pi over 2. And I'm going to take pi over 2x and set it equal to positive pi over 2. So set it equal to negative pi over 2 and pi over 2. That's going to give us where our vertical asymptotes are. So now if I multiply, let's see, multiply both sides by 2 over pi, we're going to get over here, it's just x, but over here, pi's cancel, 2's cancel, I got a negative 1 there. And then here, same thing, x, you can do your reciprocal and you should just get 1. So my graph is going to look like this. Out here at 1 and at negative 1, I have vertical asymptotes. I know because this is tangent that halfway I get that x-intercept. And now it's just a question, does it look like this or does it look like this? Well, the number in front is a positive 1, which has no impact on it. It doesn't flip it over, doesn't even stretch it. So it's just going to look like your standard tangent function. And then, yeah, that's good. Of course, it repeats itself, okay? So the question would be, what would be our next number here at our next vertical asymptote? Well, the distance between here and here is 2, right? 1, 2. So if I go 2 more over here, this should be 3. That should be a 2. And I should have another one of them like that. And then I could keep doing that, but is what it is. Okay, let's look at 23. Things are going to change here a little bit. 23. Y equals cotangent of 1/4 x. All right, we need to know what cotangent looks like. And cotangent does not look like tangent. Well, it kind of does, but there's some subtle differences. For cotangent, we don't have the negative pi over 2 and pi over 2. Instead, for cotangent, the important vertical asymptotes actually occur at pi and then at 0, which is the y-axis. And then halfway between them, pi over 2 is where we have our x-intercept. And instead of going like this, our cotangent function goes like this. So you've got to know that, okay? You've got to know that the key points are 0 and pi instead of negative pi over 2 and pi over 2. And you've got to know halfway point is your x-intercept. So I'm going to go through the same technique we've been using. I take 1/4 x, I set it equal to the first important place, which is going to give me my vertical asymptote on the left. Then I take my 1/4 x and I set it equal to the other vertical asymptote, which is pi. And then here I get 0, and here I get 4 pi. So when I go to graph this, I start at 0, I have vertical asymptote here, and then I go to 4 pi. I have another vertical asymptote. I know that halfway, which is 2 pi, I have an x-intercept, and then it's a matter of determining whether or not it goes like this or possibly like this. The only way it would do the red is if there was a negative in front, which there is not. It's just like a 1. So it does nothing. It just leaves it like this purple one. So I'm just going to draw it like this. Okay, that's it. All right, 27, -3 secant of x. Which number is this? 27. Y equals -3. Did I say secant? Yeah, I said secant. It's cosecant x. All right, now how do we graph these? Now I did this in class, I'm sure of that. So the way that I tell you to graph this is by first switching this over, realizing that this is 1 over sine, and just graphing, instead of trying to graph the cosecant, graph this -3 sine of x, okay? So we're gonna do, instead of this, this. Now let's see what happens here. If I graph that, now this is the previous section. You would take the argument, set it equal to 0 and 2 pi, and you would get, again, I'm trusting you can do this on your own. You would get your quarter points, 3 pi over 2. And then with the -3 out here, when you tested a point, you would figure out this was -3. And then you would have, this one would be +3, like that. So this would be the graph. That would be the graph of -3 sine x. And what I'll do is I'll just do one more period on here. Let's see, if this was from 0 to 2 pi, the next one will be 4 pi. Halfway there, that'll be 3 pi. Then here and here. So it's going to come down again. This, come back up, and then back down like that. Okay, so we are interested mostly from this graph figuring out where we have x-intercepts, because remembering that the original graph we want is -3 times 1 over sine x. We were trying to figure out where our asymptotes are, so I'm going to try and figure out where sine is 0. So anywhere sine is 0, I'm going to put vertical asymptotes. So this in red is going to be my final picture. There, I have an x-intercept for the sine function. There, I have an x-intercept. 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 And then I just go to the bottom of this valley here and I draw a U, a little parabola looking thing. Top of this hill, a U. Bottom of this one, a U, and then top of this one, a U, like that. All right, so the red graph right here is that. So graph this one first, make sure you got a good graph, and then just go pick off the hills and valleys here and just draw your little parabola looking things. And make sure you got your vertical asymptotes in there. All right, number 29. 4 secant of 1/2 x. $30, 29. All right, so to do this, I'm going to do the same sort of thing. Because this is secant, I'm going to have to graph cosine first, because secant is the reciprocal of cosine. So I'm going to graph first y equals 4 cosine of 1/2 x. And we've done that already. Okay, I'm going to set the argument here equal to 0, which would give me 0. Oh, it's not a point, sorry. 0. And then set that equal to 2 pi. We should get 4 pi. And then I have a midway point, that's 2 pi. Then the quarter points. Because this is a cosine function, I know that it's at the quarter marks that I have the x-intercepts, not here. That's what I was trying to say. And then I have to figure out if these 2 points are above or below. So I pick a test point like 0, plug it in here. I would get 4 here, negative 4 here, and it would go from here down, this, back up, like that. Oops, this is not my final graph, so I better do this dashed. Okay, there. Then let's continue one more period. So here's 8 pi, 6 pi, 5 pi, 7 pi, like that. And it went to here, so I'm going to have another point here, 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 and here. So I go that. Okay, so that is the graph of this. Now because I'm doing secant, which is 1 over cosine, I look for all the x-intercepts, and I draw vertical asymptotes. Like that, like that, like that, and like that. And then it's the whole hill and valley thing. Down here I should have a U like that. Here I should have a U like this. Here I should have a U like this. Here I only drew enough to draw the left half of this, and over here I only drew enough to draw the right half. So that should be the graph of 4 secant of 1/2 x. Okay, 33. Tangent of 1/4 x plus 1. So we're switching back now. We're going back to a tangent. So I'm not going to have to graph like a sine or a cosine first. Right? 33. I'm graphing a tangent. Tangent 1/4 x plus 1. Okay, we've done something like this in the past. The plus 1 is just going to move that graph up 1. So I'm going to graph that first. I realize because it's tangent that there are really like 3 important points. The negative pi over 2 where I had a vertical, the pi over 2 where I had a vertical, and then the middle 0. So I first start by setting 1/4 x equal to negative pi over 2. Then I set 1/4 x equal to pi over 2. This will give me x is equal to, let's see, multiply both sides by 4. You get negative 2 pi, and then here multiply both sides by 4, you get 2 pi. So I've got a picture that looks like this. Here's 2 pi, here's negative 2 pi, and I know that I've got vertical asymptotes here. I know midway I'm supposed to have an x-intercept. And then because this is a 1 in front, I know it's just going to be your standard sine curve, which should look like this. Now I'm doing it dashed because there was one more element I needed to add to this. I needed to do the plus 1. So that means every point on this graph moves up 1. So instead of really having an x-intercept here, it's going to move up 1. Every point moves up 1. So it's going to wind up looking like this. Okay? There you go. That's it. Number 39. Number 39. This is a good one right here. 39. Y equals 2 cosecant of 1/3 x minus 1. All right, so this right here, minus 1, is going to move the whole graph down. It's going to move that graph down by 1. So I'm first going to start by looking at just this graph. And to do that graph, because it's cosecant, which is 1 over sine, I'm actually going to be looking at y equals 2 sine of 1/3 x. Okay, again, I'm not taking into account the minus 1 yet. Now I go through my game. It's a sine function, right? So I'm going to be doing some important points. I'm going to set that equal to 0. When I do that, I get 0. Set that equal to 2 pi, I actually get 6 pi. Then I can do my important 4 marks here. My total, it's actually 5 marks, 4 little intervals. Halfway is 3 pi. Halfway between there and there, that's 3 pi over 2. And then that's going to be 9 pi over 2. Okay, so that's, wait, what the heck am I doing? Yeah, no, that's right. 4.5, yeah, okay. 1.5, 3, 4.5, 6. Okay, so those are my points. Now it's a sine curve, so I know it's supposed to go here, here, and here. And then I could pick a test point like this and plug it in and figure out that it's actually going to go up to -2. So it should start here, and then at this point it should end here. So I'm going to have something that looks like that. Okay, that's my sine curve. I could continue it over here if I wanted to. This would be what, 12 pi? And then that would be 9 pi right there. That should be enough. Go up, down, back up like that. Okay. Now, let's try and start getting this together. Now, let me, again, ignore the -1 because it's cosecant, it's reciprocal, 1 over sine. I'm going to go to all my x-intercepts and draw vertical asymptotes. And finally here. Now the little peaks and valley game. Go to this one, I'm supposed to draw a little U. So I'm gonna do it, draw a little U, but I'm doing it dotted because I've got to still move everything down 1. So here, a little U, that, this one a little U, that, and this one a little U, like that. Now I'm ready for my final picture. So all I'm gonna do is take that picture in red, which is this piece right here, and move everything down 1. So I'm just going to grab this point right here that used to be at 2, move it down to 1, and I'm going to draw my U like this. This point that used to be at -2 is going to now go to -3 and go down. This point that was at 2 comes down to 1, and then I draw my U. And then this one comes down 1 to -3, and I draw my U, like that. So if I erased all that other junk in there, right? So if I took out all this, see those vertical dotted lines are there for reference. They're not technically part of the graph. They're there to just remind us that's a vertical asymptote. You know, that in purple there is the graph. All right, how am I doing here? 39? That was 39. All right, I'm done.